Welcome. So today we are pleased to introduce Emilie Stewart-Jones, who will be speaking about her research on rock walls of Western Canada, evaluating the relationship between permafrost, topography, and climate. Emilie has recently completed her MSc at Carleton University, working as a part of NSERC PermafrostNet. During her undergrad, she spent her summer analyzing and managing ground temperature data and conducting fieldwork in northern Canada. She completed a Bachelor of Science with honors in physical geography and earth science in 2019, with a research project focused on ground surface temperature variability in Lac de Gras region of Northwest Territories. After graduation, yearning for mountains and wilderness, Emilie moved to Whitehorse, Yukon, where she played a large role in the development of the Yukon Permafrost database, a publicly accessible web application for permafrost-related data. Emilie's master's work investigated the relationship between rock wall temperatures, topography, latitude, and continentality. In addition, she tested a new method for modeling ground rock temperatures in remote locations, which can be used for evaluating rockfall events and assessing rockfall risk.
So I'm presenting on my master's research, which was focused on permafrost in rock walls and its relationship to topography and climate. But I'm also going to show some stuff that I've been working on since completing the writing of my master's, where we played around with applying this ground temperature modeling workflow that I use in my thesis to locations where rock falls occurred to sort of analyze them. So this is a photo from Tombstone Territorial Park. This is very close to some of my field sites. I have some field sites on the mountain in the back, and then on the one the photo was taken on. A bit of context: when I say rock walls, what I really mean is very steep bedrock, like you can see in this photo here. This is actually another one of my field sites on Canoe Mountain near Valemount, BC. And if you look closely, you can see a little red person there who's installing some sensors. They're well attached with ropes. So the reason that I'm interested in all this is because there is a pretty clear link between climate change, permafrost degradation, and slope instability, and that's definitely the case for steep rock faces. So it may not be obvious when you think of bedrock, but there's lots of cracks and crevices, as you can see in this photo. And those cracks and crevices can be filled with ice. So if the air warms or we get an increase in precipitation, we can get warming of the rock, melting of the ice in those cracks, and then we can also get more water infiltration, and this can cause the steep rocky slopes to weaken and eventually fail. So these are two examples of some rockfalls that have happened recently in permafrost areas. So the photo on the left is of a large rockfall that occurred at Mount Joffre, which is near Pemberton, BC, southern BC. And this is a very popular backcountry recreation area. There's actually a little hut right here that people go and stay at, and they would use this valley to access it. So this is a research paper by Frail et al. As published in 2020, and they estimate that permafrost degradation over the previous decade, combined with really warm spring temperatures that we had out in Western Canada in 2019 in the spring, that resulted in the failure, which was a pretty big failure. And then the photo on the right is of Mount Jean, which is above the Tack River, which is near Atlan, BC, which is in BC. This happened a couple of years ago in December. It's hard to grasp the scale of this rockfall, but the top here is about 1.5 kilometers above the valley bottom of the Tacky River. Pretty large rockfall. And then for both of these rockfalls, each of them, the rock that was released was about the weight of 100 CN towers. Lots of rock came off of the slope. And this photo on the right, this is the Tacky River, which is an important river for the Tacky River Tlingit First Nations, because that's where they harvest salmon, and that's also where they have a business selling that salmon. To understand and to efficiently assess the potential hazard of rock falls in an area, we actually need to have some sort of idea of where permafrost exists and how it's changing. And that's something that's currently mostly unknown for a lot of the areas of a lot of the permafrost mountain regions of Western Canada. And permafrost in rock walls is highly dependent on topography. We can kind of use topography to figure out where permafrost is and what state it's in. Lots of research has been done on this, but not in Western Canada. Lots of research looking at that relationship between climate, topography, and rock walls has been conducted in Europe and in Scandinavia, but not in Western Canada. And that's sort of the gap that I'm trying to fill here. My research, I've really focused my thesis on surface offsets, and I use surface offsets. So surface offsets are the difference between mean annual air temperature and mean annual rock surface temperature. Air temperature is generally higher than the rock surface temperature, so we have these positive surface offsets. And the reason that I'm looking at surface offsets is because it gives the effect of topography on rock temperatures. So it very conveniently expresses that spatial differentiation we get in mean annual rock surface temperature, which can then be used to assess permafrost. So I'm going to quickly go through the important factors that affect permafrost in rock walls. And this is mostly based on research that was conducted in the Alps and in the mountains of Scandinavia. So one of the main things when it comes to permafrost in rock walls is that it's mostly affected by air temperature and solar radiation, which I mostly call shortwave incoming radiation in my research. And that's because, well, of course, air temperature affects the temperature of the rock, and then the radiation, there's more radiation that warms up the rock. Okay, so when it comes to aspect, research has shown, it's pretty obvious if you think about it, south faces are typically warmer than north faces, and that's because they receive more of that solar radiation. One thing that the research has shown is that at higher latitudes, there are smaller differences in temperature between those north and south faces. And that's really because, for one, there's less radiation in the summer, but also there's less difference in radiation in the summer between a north and a south facing rock face because the sun is lower in the sky and has a larger arc. So there's actually some sun that's hitting those north faces. And then so previous research has shown, for example, that in the Alps, the difference between a north and a south facing rock face is the temperature is around 6 to 8 degrees Celsius, and that's at around 46 degrees latitude. And then Norway, which is between 60 and 70 degrees latitude, we have differences of 1.5 to 3.5 degrees, so it's getting smaller. And then Ellesmere Island, where you're at about 80 degrees latitude, you're getting much smaller differences between north and south faces on the order of 0.5 to 1.5 degrees Celsius. Another important factor when it comes to topography, elevation. So mainly it's just the fact that if you're at higher elevations, you are receiving more solar radiation because there's less interference from the atmosphere. So at higher elevations, you're going to get higher surface offsets. And then when it comes to slope angle, generally we have increasing surface offsets with decreasing slope angles. So if we have a shallower slope angle, we're going to get more radiation just because there's more direct sunlight. But research has shown that this trend may reverse at higher latitudes, mostly because the sun is lower in the sky and there's less solar radiation. Another thing that I've looked at, so when I'm talking about climate, I'm often talking about continentality and latitude, which are kind of two predictors of climate. So continentality is essentially a measure of the effect of the proximity to a large body of water or ocean. A more maritime area will have less extreme air temperatures and will generally be more cloudy. So in this study, continentality is expressed as the annual amplitude in mean monthly air temperatures. That would mean the difference between the mean temperature of the warmest month, typically June or July, minus the temperature of the coldest month, which would typically be January. So it hasn't been, in previous research, there hasn't been conclusive research on really the effect of continentality on rock temperatures or surface offsets. But you can kind of assume that if it's more continental, you have less clouds, and so you have higher surface offsets. And then some research has research has generally shown that high surface offsets are found at the most sun-exposed sites. So those at high elevations, self-facing, and low cloud cover, which is probably those with a high continentality. Another factor that unfortunately I didn't consider in my master's, and that's that the fact that these rock walls are not perfect. There's lots of imperfections, cracks, joints, and these can cause snow to accumulate and also increase ventilation, which can have an effect on rock temperatures. To explore these relationships between topography, climate, and permafrost and rock walls, I used a modeling approach to allow me to extrapolate beyond the few observations that we have in Western Canada. I use a modeling workflow for simulating ground temperatures. And when it comes to modeling permafrost and rock walls, there are two main methods that have been used. This is very much a generalization, but the first would be statistical modeling. A statistical model typically will find the statistical relationship between both like potential radiation, air temperature, typically mean annual air temperature, landforms that are indicative of permafrost, and observations of permafrost or temperatures. And then you can use this to estimate permafrost probability over a larger area. The limitation of this type of modeling is that it can only really be applied within the region of study, so within the area that you have rated it for. And then, but the advantages are that you can model over a pretty large scale or large area with relatively little computation. So if you look at this plot or this map on the right, this is a statistical model that was used to create a permafrost probability map for Norway. And then for physical modeling, so physical models predict rock temperatures at depth from climate data using physically based calculations. So limitations is that it can be pretty computationally intensive, so it's harder to do that over a large area or over a lot of points. The advantage is that, well, there's a number of advantages. It can be applied anywhere in the world where data is available because it's using physically based calculations, which don't change where you go. And it also accounts typically for temporal variability because you're using M-series climate data as your input. Really, the limitation for all of these modeling techniques is that the accuracy or the precision or the resolution of your output is always going to be limited by what you have as input. And typically we're limited by the availability of data, which is definitely the case in Western Canada. This is my modeling workflow that I use for simulating rock temperatures and surface offsets for my thesis. To deal with the lack of driving data and the uncertainty of it, I have used an ensemble of reanalysis data. So reanalysis data is climate data that's modeled from climate observations, and this data is available globally. I use a software called GlobSim, which was developed within our research group, which allows us to downscale climate reanalysis data from multiple sources to a point location. I have 3 different climate reanalysis, which I was able to downscale to point locations that I was interested in. And then I'm using a physically based model called Geotop because it allows me to output hourly data and I can specify physical characteristics for each site that I'm interested in. I'm using this model to simulate temperatures at point locations. This model, the first step is to evaluate it, to test it. So I've tested it with rock temperature observations from 4 locations across in the Yukon. So those are shown with these black dots here in the map. And this gives me a total of 36 stands or sites where I have rock temperatures. And then the next step is to evaluate the effect of topography and climate on permafrost and rock walls. The surface offsets are simulated for 9 locations, which are shown with these blue dots here. I evaluated the model with, as I mentioned, those 4 locations, and each of those has a number of sites that are measuring rock temperature using these sensors that you see in this image on the right. So these sensors measure rock temperature every 20 minutes, just 10 centimeters below the rock surface. And they're installed. So this one was installed from the ground, but most of them are installed from the top by rappelling down and installing the rock face. So I have a number of rock temperature loggers at each of my testing sites. So these are the results from the model testing, or some of the results. So I have 4 plots here, each of them for the different model testing locations. And then each of these points are within the plots are mean annual rock surface temperature, where I have modeled mean annual rock surface temperature against observed mean annual rock surface temperature. Ideally, these would follow a perfect line, but of course it's not perfect, and that's not what happens. Each point is for different sites and different years, and then I've colored them differently for the 3 different reanalyses. The reason I color them differently for the 3 different reanalyses is because I want to show that there is quite a bit of variability between the 3 reanalyses, and that's why it's a really good idea to not just use one, but to use multiple, which is what I've done in this project. So here's like a pretty extreme example. We have like over around 5 degrees of variation between reanalyses. That's not always the case, but it is for that site. This is a plot there where I have all of locations in a single plot, and I averaged the results for the 3 reanalyses. And then each point is for different years and different sites. And then I have a line, which is the line of best fit for each location, each of the 4 locations. One thing we can see is that there's a pretty variable bias between different locations. Some of them are negative and some of them are positive. Another thing that we can see is that the line of best fit is a steeper slope, which tells us that there's more range in mean annual rock surface temperature values for the modeled results than the observed results. And then another thing that we can see is that the warmer sites typically have a warmer bias. The extreme example here is for Canoe, where these warmer locations are very positively biased. That tells me that the modeling work will produces a warm bias for the more sun-exposed sites. So despite these shortcomings, one thing that I think this model does do well is that there's some pretty good correlation here, which tells me that the modeling workflow does capture that fine scale variability, which makes it suitable for simulating surface offsets. It may not be super accurate at simulating rock temperatures themselves, but at simulating the difference between rock temperatures, it's doing a good job. Another thing is that because there's quite a bit of variability in fit between the different locations, that tells me that it's a really good idea to test your model with multiple locations, because you're going to get different results. So the next step, once I've tested the model, now I can run the model. I've simulated surface offsets for 9 different locations, and these 9 different locations, which are shown in these blue dots, are meant to represent the range in climate, which is both continentality and air temperature, across the mountains of Western Canada. And then for each of those locations, I have 3 different driving data sources, so the 3 different reanalyses, and then I'm modeling for 3 different slope angles, 9 different elevations, and 4 different aspects. And then here are the results. This plot sort of packs in all of my results or most of my results into one plot. We have the color that you see is for surface offsets. And then the different rows here are for the 9 different locations. And then the columns are for 5 different elevations. And then we have 3 different slope angles and then 4 aspects down here. So one thing that we can see that's pretty obvious in terms of aspect is that the highest surface offsets are on the south faces, consistently on the south faces for each location, and they're consistently the coldest or the lowest on the north faces. One thing that is interesting, though, and that I didn't expect, is that the east faces are consistently warmer than the west faces, which is pretty interesting. And these are often by considerable amounts, like 2, 3, 4 degrees. Another thing, if we look at elevation, so typically surface offsets are getting stronger with elevation. Let's say here at 500 meters, the north face is relatively cold, but then it gets much colder or has more lower surface offsets at higher elevations. And then the opposite is true for south face. where the surface offsets get higher as you go up in elevation. And the last thing to look at is slope. Slope has less of an effect than aspect and elevation on surface offsets. Really, the greatest variation can cause within a location is 1 degree. But typically, what I've seen is that the 70-degree slopes are the warmest. So here is basically the same plot, but instead of surface offsets, we're looking at solar radiation. And really what we see is that the surface offsets follow the solar radiation pretty well. One thing that I noticed is that there's some larger, more obvious differences between slope angles where the shallower slope is consistently has more solar radiation than the steeper slope. Bringing it back to something that I mentioned at the start, which was that the north-south differences are smaller when we are at lower altitudes. So this plot here, I have the difference in surface offsets between a north and a south face, and then I have latitude on the x-axis, and then the different circles here are for the 9 different locations, and then the numbers within them are the continentality values for that location. But we see that there's not like a clear line where if we're at lower or higher latitudes, we have lower difference between north and south faces. What we see is that there's quite a bit more variability than that. Within these 4 locations, we do see that where there's similar continentality, there appears to be some sort of relationship, but otherwise it's not as clear for the other sites. One thing that we do see is that where we have this very similar latitude, so let's say for South Interior and South Coast Mountain here, similar latitudes, but South Interior has higher continentality, then we see higher difference between North and South faces. So this is really just telling me that it's not just about latitude, it's also about locality. And any sort of relationship between surface offsets and continentality and latitude, really in the end, they just come down to the amount of direct, or they come down to the amount of solar radiation. So these 2 plots just show surface offsets against solar radiation. And you can see that there's a pretty clear relationship where we have higher surface offsets, there's more solar radiation. And that's really why continentality has an effect, or appears to have an effect. Okay, something I've done, this is not part of my thesis, this is something I've done since I finished my thesis, and it's really just exploratory work I've done using this modeling workflow that I've tested and used in Western Canada. So really what I've done is I've taken locations where rock falls have occurred. So if you remember from the start of my presentation, I talked about Joffrey, where there was a large rock fall in May 2019 on the north face. Using this modeling workflow, I can model rock temperature to simulate rock temperatures at the lower, or at the higher end of the higher elevation of the scar, and then at the lower elevation of the rockfall scar, and see how those temperatures have changed in the last 40 years, of 1980 to 2021 here. And then this red line here is actually when the rockfall occurred. And we also see the range between the 3 reanalyses in gray. So we can see for this site, as was mentioned in the paper that I mentioned on the Joffrey rock slide, there is a pretty clear increase in rock temperatures over the last 40 years. Another application here is you can look at finer temporal scale. So again, I have the lower end of the rockfall scar and then the higher elevation end of the rockfall scar. And then I have east, south, west, north. And these are rock temperature time series between 1990 and 2022, where when the temperature exceeded the previous maximum temperature over 7 days, I have it noted with this red line to show that it's like a new maximum temperature. So there's quite a few new maximum temperatures, especially on these north faces, and then a lot in that heat dome that happened in the summer of 2021. I haven't really done much analysis of these, and this is just mostly to show like the potential of this tool for evaluating change in rock conditions. So really, this research is the first to look at surface temperatures in rock walls over a really large range of climates and topographies and latitudes. And I think that it has presented some new insights on the relationship of rock temperatures to continentality, which other research hasn't really been able to do. Also, it's demonstrated the use of this modeling workflow, and it's shown that I can use this modeling workflow for modeling rock temperatures. And the reason it's so powerful is because it doesn't require climate observations at the site of interest and can really be applied anywhere in the world because it uses climate reanalysis data. And I've also shown that it's suitable for research that requires reproduction of fine-scale spatial and temporal variability. Future research possibilities, I think in this project, I've really just focused on these steep rock faces, but there's nothing to say that this modeling workflow can't be used for different types of sites. So like gentler rocky slopes or vegetated slopes and mountains. Another possibility is to look at how temperatures in steep bedrock have changed over previous decades, sort of what I've shown in those plots at the end, and then how they might change in the future and what that means for rockfall risk. Another thing is that I can use it to evaluate temperature trends leading up to rockfall events. So yeah, that's basically it.
Thank you so much, Emilie, for the presentation. It was a really interesting work, and thank you for sharing it here.
Emilie, you've said that the surface offset is most strongly tied to the shortwave radiation that the slopes receive. And if you were to think about slightly less steep slopes and you were to switch on the snow cover, do you have any ideas what peculiar effects might arise from that with respect to continentality or north and south differences?
Yeah, I mean, it would change things quite a bit because depending on the depth of the snow, you can actually have different effects of radiation. So if you have, a lot of snow, then that can warm the rock because you're insulating from the air. But if you have just a little bit of snow that protects from radiation, then that can actually have a cooling effect. And then also that depends on, and the amount of snow will depend on, continentality. And these effects would also depend on, latitude and how much radiation you're receiving. So yeah, it would definitely make things a lot more complicated.
Thanks.
Very nice, Emilie. I'm thinking about, sometimes we get these winter rock slides like Taku and Mount Steele and La Perouse and things like that. And then we get a lot of spring or summer events, right? So Joffrey was an example where we had two closely spaced events 3 days apart, and the canoe event near Bruce Jack, and those seem to be very closely tied to an immediate, like a really warm period. But the other ones are obviously have more delayed responses. So can you speculate a little bit about what might be going on in those situations?
In the ones that are happening in the winter?
Yeah. Or both, in both cases, but like, is there something different going on? Like they seem to be similar rock volumes involved. And
well, though the ones that are happening in the winter, often they seem to be the result of, from what I recall, oftentimes it's somewhat warmer temperatures, or the temperatures have been warmer in like previous years, and then in the weeks preceding it's warmer than usual, and then you actually have a dip in temperatures before the event happens. So from what I understand, that is the result of possibly water that's infiltrating and it's getting deeper than it used to be able to go because we have a melting occurring, and then it expands when we get that cooling. But yeah, I'm not really sure if I can answer your question. I think from what I've seen is that it's super, super complex and there's like a lot of different variables. But I do think that it could be really interesting to use this tool. So the plots that I showed was just looking at maximum temperatures throughout the year, but could be interesting to see, like, this week relative to this week over the last 40 years, how does it compare? Maybe you would see that in those events that happen like in December, you're not getting extremely warm temperatures because you're in December, but you are getting warmer temperatures than you would typically at that time of year. So I think that would be cool to explore.
Yeah, I think so too. Thank you.
I have two questions, Emilie. One sort of follows up on Martin's question there. There's been a number of these rockfalls in BC, and depending on the timing, like you say, there might be a temperature dip after the warm period, or one in eastern BC fairly recently. It didn't happen until sort of later in the season. There had been a very warm period and then it cooled off. And my interpretation of that is that you have this big warm signal, and as we know, it takes a little bit of time for that temperature signal to get sufficiently deep into the ground, or into the rock in this case. So I'd be curious to see, in the cases of these events, is there any analysis of what the timing is of these temperature maxima penetrating into the rock or the ground? And like to what depth, are they going into a greater depth, or what's the relationship between that propagation of the temperature maxima into the rock with some delay? Have you found any?
I haven't had the chance to do that, but that's obviously something that would be really interesting. I know that from what I remember, some research has looked at that in the Alps, and they looked at timing of events and when there was warming. And there was different scales to which it was, but I don't know if they actually compared it to the depth of the rock walls. Yeah, but that would be super interesting to look into.
Then the other question, and it's a more of a broad permafrost research question. You've looked a lot at permafrost now in Western Canadian mountains, and from what I understand, there's a lot less work that's gone into permafrost in that region. Have you identified any sort of big questions for permafrost in that area that really stand out as gaps when you compare to something like the Western Arctic or these very well studied regions?
Well, I think one of the obvious things is like most of this research has been in mountain areas where there aren't really any trees or vegetation. And obviously with this project, I avoided the trees and the vegetation, but that's definitely a big gap in Canada, where there's a lot of like steep mountain permafrost where there's vegetation and there's trees, and there hasn't been a lot of research into that.
Thanks.
Emilie, I also have one question, maybe not very related to your presentation, but the question is, you showed that what you modeled and the observation were kind of, for some areas, they weren't very close to the perfect line. And I wanted to know if you have encountered any research that they have updated the model based on the observation they have seen, like these Bayesian kind of analysis, like you have some observation and you can do some updates based on the observation, so to get a better model to work with.
Yeah, to be honest, I don't know much about that. What I understand is that it's difficult because it changes depending on where you are. You're not always seeing the same biases with different locations. So I don't know. Maybe Stefan can add to that. But from what I understand, it's difficult to do this.
I also don't know if it's possible or not. I just asked the question out of curiosity. So
assuming, just to jump in, I think there might be some merit very locally where you have measurement clusters to, essentially calibrate your model, right? To say, hey, if we're doing the shortwave in a different way. The problem, though, is that we have so many dimensions of variation here, and we don't really know where some of the errors come from. I think the problem's always going to be overfitting, which means we're becoming less honest and we're looking away from the actual amount of variation that exists around our modeling result. And I think if you look at most other permafrost modeling studies, there are very few observations used in very few different places, right? And normally it's very difficult to really see what is the skill of a model to predict spatial variation and temporal variation. And so I think in a first step, it's just great to show this and be frustrated or not, right? And then we can fit it But I think it depends on the application you want to have. And it might just make us more blind to imperfections.
Once again, thank you, Emilie, for being here, for presenting your work here. And we appreciate your time. And it was really interesting work. Have a good day, everyone.